In the today's video, we go with the covalent bond, how covalent bond is formed, at the same time what are the types of covalent bond present and how to find out the type of covalent bond. Several things that should be discussed in the today's session. And let us see the covalent bond. So in case of a covalent bond, where bond is formed, bond nothing but force of attractions between the two atoms. Okay. So here bond is formed by sharing of electrons. Either one or more electrons between the two combining atom. So in this case, bond formed between two atoms or a two combining atom by sharing of either one or we can say more than one electron. Maximum 3, not more than that. Okay. So sharing of one or more electron between two combining atoms, thereby bond formation taking place. That is nothing but a covalent bond. So normally this covalent bond taking place between non-metals. Okay, the point we know that between two non-metal where covalent bond formation taking place. Hydrogen and hydrogen, hydrogen and chlorine, hydrogen and fluorine, hydrogen and oxygen. Like that, between two non-metal, the bond formation taking place is the covalent bond. And point we know that this covalent bond is directional in nature. What the meaning of directional? On particular axis is there, either x-axis or a y-axis or a z-axis. But in case of an ionic bond, not a direction. There is no any particular direction, non-directional. All ionic bonds are non-directional. Because ionic bond is the bond where force of attraction between two charged species. The charged species may attract in any direction. There is no particular axis. As a result, the ionic bonds are non-directional, whereas covalent bonds are directional in nature. And for ionic bond, there is no proper symbol representation, but for a covalent bond, the hyphen is written. So, for example, A bond B, like that. So, this hyphen indicates for the covalent bond. Suppose one hyphen is there, then you consider as a one covalent bond. Suppose if two hyphens are there, then consider as a two covalent bond. Suppose if three bonds are there, three lines are there written, then it is considered as a triple bond. So one line single bond, two line double bond, or you can say three line triple bond. So these lines indicate the symbol for representation for a covalent bond. Here let us say one bond is there between atom A and then atom B, and these two atoms are non-metal in nature. Okay, this is the definition or a meaning of a covalent bond. So sharing of electron between the two atoms, thereby a covalent bond formation taking place. Either one electron or more than one electron, thereby bond formation taking place is nothing but covalent bond. Now let us go with an example. So I have one example, that is formation of H2 molecule. H2 hydrogen molecule. And first in the beginning in the last classes I said to write the any bond or a type of bond formation you must write electronic configuration. Here two hydrogen atoms are there. Let us say this is the first hydrogen, this is the second hydrogen, and its atomic number found to be 1. Here also atomic number of hydrogen is taken as a 1. And if you write the electronic configuration, 1s1 is the electronic configuration for this hydrogen, and 1s1 is the electronic configuration for the next hydrogen. That means both hydrogen are same atomic number, same electronic configuration. And if you write the electron dot structure tells about total number of valence electrons present. Okay, total number of electrons present in the valence shell or outermost shell. Okay, outermost shell or outermost orbit. Here that first itself is the outermost shell and one electron present in that outermost shell. So that is symbol represented as H, one dot. Here also H with one dot. So one dot indicate only one valence electrons are there. Now tell me, so this hydrogen need one more electron to show 1s2 configuration. Similarly, this hydrogen need one electron to show 1s configuration. In this case, both hydrogen atoms need one electron. As a result, in that situation, that hydrogen atom will never donate or never receive. In the previous discussion, that is in ionic bond, one atom ready to donate electron becomes cation. Another atom ready to gain that electron becomes anion. That is a donation and gain of electron, that type transfer of electron possibility observed in ionic bond. But in covalent bond, the transfer not possible. Here, this need one electron, here also it will need one electron. In such a situation, the two atoms need electron. If it is the situation, now mutual sharing taking place. How it is shared? So this electron electron need for this hydrogen. So this electron shared by this hydrogen atom, sharing the limit force of attraction by the nucleus. And this electron shared by this hydrogen atom. Thereby, the two electrons are controlled by the two nucleus. One nucleus of hydrogen, other one is the nucleus of another hydrogen atom. So thereby, one electron from each combining atom. One electron from this hydrogen, another electron from this hydrogen, or simply one pair of electrons are involved in case of a sharing. So thereby, sharing of electron, here one electron, in that combined atom, thereby bond formation is nothing but hydrogen bond. Since one electron from this hydrogen, another one electron from this hydrogen involved, so as the bond formation taking place between these two hydrogen atoms are covalent bond. And how many covalent bonds are observed? Only one covalent bond. Since one electron from each combining atoms are involved, or in other words, one pair of electrons are involved in this sharing. That is why one covalent bond formation taking place. So thereby the molecule formation formula is called H2. H2. If you add these two, then we can see this H2. So that is the one of the example, formation of a hydrogen molecule. If you go with another example, formation of a HCl. Look at that, hydrogen and chlorine are the two atoms present. In hydrogen atomic number 1, but for chlorine atomic number 70. That means electronic configuration for this hydrogen 1s1, and for this chlorine its atomic number 17, electronic configuration 1s2, 2s2, 2p6, then 3s2, 3p5. So this is the electronic configuration for chlorine. Now, what is the electron dot structure? How many electrons present in the valence shell? So, in case of hydrogen, already you know only one electron, that itself is present in the first shell, and H with one dot is the electron dot structure for the hydrogen. But in case of a chlorine, look at that. First is the inner shell, second is also inner shell, but 3 is the valence shell. Outermost n value is going to be highest n value is going to be this 3 in this case. And 3s to 3p5 is the valence shell electronic configuration, and total number of electrons present in this valence shell electronic configuration is 5 plus 2, total is 7 electrons. So 7 electrons are present in the valence shell, and those from 3s orbitals, 3p orbital. So 5 plus 2, total is 7 electrons are there, and we have to put 7 dots surrounding to that chlorine. So this is the chlorine atom, then 1, 2, 3, 4, 5, 6, 7. Total 7 dots one can find. Okay, out of which 2 from 3s, 5 from 3p. Now this is the electron dot representation. Now carefully also, whether any element is ready to donate or any element is ready to accept electron. So this is the hydrogen, it will need one electron. If it is take one electron, it becomes 1s2. That is a stable electronic configuration similar to that of helium. So that is why it is not ready to donate. Okay. Similarly, chlorine, it has totally 7 electrons. It will need one electron. There is a shortage of one electron. If take one electron, it shows octet state, 8 electron present in the valence shell. And also, if it is receive one electron, it becomes 3s2, 3p6. Has a ns to np6 stable noble gas configuration. If that is the situation, then what happens? Both need electron. If that is the situation, so this chlorine share the electron of hydrogen. Similarly, hydrogen share one of the electron from the chlorine. Out of 7, 1 electron from the chlorine. As that 1 electron from the chlorine shared by the hydrogen. Similarly, only 1 electron is there, and that electron of the hydrogen shared by the chlorine. As that these two electrons, one from hydrogen, another one from chlorine, mutually share, so thereby the bond formation taking place. Since only 1 electron pairs are shared from these two, as that one covalent bond formation taking place. So H single bond and chlorine. So thereby HCl formation taking place. So this is the way how the HCl bond formation are taking place. Similarly, in the formation of oxygen molecule, there are 2 oxygen atoms are present. Atomic number of oxygen is going to be, it is 8, okay, and electronic configuration 1s2, then 2s2, after that 2p4. And then in case of here also same electronic configuration 1s2, 2s2, as well as it is 2p4. Okay. And if you find the electron dot structure, 2 is the valence shell, and then 2s2, 2p4 is the valence shell electronic configuration. Here also 2 is the valence So oxygen is present here at the center, and then total number of valence electrons 4 plus 2, 6 electrons are there. 1, 2, then 3, 4, 5, and then 6. Similarly here also there is an oxygen, and where we find totally 6 electrons present in the valence shell. So this is a 2 electron, 4th electron, 5th, 6th, 4th, 5th, and then 6th electron. So totally 6 electrons are present in valence shell. Now carefully observe whether it is stable. No, this oxygen is less stable. Why? Because they are not satisfying the condition for stability. What the condition for stability? It should show, an atom should show. Why atom will form bonding? Atom should form bonding because two reasons. One, to attain noble gas configuration, that is NH2 NP6 configuration. Another one, to attain octet state, 8 electron present in the valence shell. So these oxygen not in a stable. That means totally 6 electrons are there. It need 2 electrons. Here also this oxygen need 2 electrons. If we take 2 electrons, that become 2s2 2p6 noble gas configuration or octet state. So both are in a situation to receive electron, not to donate electron. In that situation, if these two atoms are brought into contact with each other, mutual sharing of 2 electron taking place. So it will need 2 electron. This also need 2 electron. So in order to satisfy the octet state as well as stable configuration, this oxygen ready to share its 2 electrons. So these 2 electrons are shared by this oxygen atom. Okay, these 2 electrons are shared by this oxygen atom. Similarly, it is observed that from this oxygen, these 2 electrons are shared by this oxygen atom. So these 2 electrons are shared by this oxygen atom. Look at that. So this oxygen shared their 2 electrons with another oxygen, and this oxygen shared their 2 electrons with another oxygen atom. As a result, these 2 electron pairs, these 2 from one oxygen, remaining 2 electrons from another oxygen, 2 electrons are shared. If you write clearly oxygen and oxygen, so here 1 electron, here 1 electron, there is a sharing and 1 bond formation, and another electron from these 2 oxygen share, that will produce another bond. Since 2 electrons are involved in bonding from each oxygen atom, number of covalent bond formation taking place between oxygen atoms are 2. In case of hydrogen, in case of HCl, 1 electrons are shared. That is why single bond formation or a single covalent bond formation. But in case of oxygen molecule, from each oxygen atom, 2 electrons are shared. That is why a double bond formation taking place. 2 covalent bond, or simply we can say double bond. 1 covalent bond called single bond. So here double bond formation taking place, and if you add this to them, it is considered as a O2 molecule. So in case of an oxygen molecule, 2 covalent bonds are observed. Okay, double bonds present. And let us go with one more example, that is formation of a nitrogen molecule. And if you go for nitrogen, there are 2 nitrogen atoms are there. Its atomic number found to be 7. Okay, and the electronic configuration 1s2, then 2s2, after that 2p3. So this is the electronic configuration of one nitrogen. Similarly, 1s2, after that 2s2, then 2p3. This is the electronic configuration of another nitrogen. And here 2 is the valence shell, and 2s2 2p3 is the valence shell electronic configuration of this nitrogen. Similarly here also 2s2 2p3 is the valence shell electronic configuration of that nitrogen. And if you write the electron dot structure, the nitrogen is present, and totally 3 plus 2, 5 valence electrons are there. Here totally 3 plus 2, 5 valence electrons. So after which I will write 2 here and remaining 3. Okay. Then here also nitrogen 2 valence electron, and then remaining 3 valence electron. Now tell me whether they are in a stable state. No, because they have only 5 valence electron. It needs 3 more valence electron to satisfy octet state as well as stable noble gas configuration. If that is the situation, if these 2 atoms brought into contact with each other, there is a mutual sharing of electron takes place. How it is shared and how many electrons get shared? The 3 electrons from this nitrogen shared with nucleus of this nitrogen atom. Okay, 3 electrons from this nitrogen shared with this. Similarly, the remaining 3 electrons of this nitrogen is shared with this nitrogen. That means totally 3 electrons from each nitrogen atom mutually sharing taking place. Okay, so thereby produces nitrogen and then nitrogen. One electron from nitrogen, other one electron from nitrogen, there is a one covalent bond. Second electron from nitrogen, another one electron from the nitrogen, there is another covalent bond. Third electron from this nitrogen and third electron from this another nitrogen. They mutual share takes place, thereby produces another covalent bond. So as to that, in case of a nitrogen molecule, 3 covalent bonds are there. And that 3 covalent bond is nothing but triple bond. Okay. So if you write it in a N2 formation. So here it is observed that in H2 one covalent bond and in HCl one covalent bond, but in O2 2 covalent bond, and in case of nitrogen 3 covalent bond. Or simply we can say hydrogen molecule contains single bond, HCl molecule contains again single bond, oxygen molecule shows double bond, and nitrogen molecule shows triple bond. So like that, by sharing of electron, there is a formation of a covalent bond. So covalent bond may be either single bond or a double bond or a triple bond, but 4 bond, 5 bond will not form. So maximum number of covalent bond formation taking place is 3, not more than that. So this is the way where covalent bond is generated. Students, there are 2 categories of covalent bonds one can find. Okay. So based on the overlapping of atomic orbital, there are 2 categories of covalent bonds are there. So this classification mainly done based on overlapping phenomena. Overlapping of atomic orbitals. So based on the overlapping of atomic orbitals, there are 2 categories of covalent bonds are there. The one is called as a sigma bond. The first type of a covalent bond is nothing but the sigma bond. Symbolic representation sigma. This is the way of representation sigma bond. Another one is called as a pi bond. So another type of a covalent bond is pi bond. Symbolic representation is pi. Okay. So pi bond and sigma bonds are the 2 important types of a covalent bond that is classified based on the overlapping of atomic orbitals. Okay. And in case of the sigma bond, how it is generated? It is for actual overlapping of atomic orbitals. So it is formed by axial overlap, axis to axis overlap, x-axis orbital overlap with another orbital with x-axis, an orbital with y-axis overlap with the orbital with again another orbital with y-axis, an orbital with the z-axis overlap with another orbital present in the z-axis. That means axis of overlap must be same. That is called as an axial overlap. It is observed in sigma bond. Okay. And in case of a pi bond, there lateral overlapping is observed. Not along the axis, in between the axis, lateral overlap taking place. And we will see how actually lateral as well as axis overlap taking place. So here lateral overlapping of atomic orbital makes pi bond. And if you go with respect to sigma bond, among sigma and pi bond, if you find the stability or strength, this sigma bond is very strong, whereas pi bonds are somewhat weak. So pi bonds are weaker, or lateral overlapping is weaker, whereas the axial overlapping next to the sigma bond is stronger. And if you find out the type of a axial overlap next to sigma bond, there is a S axial overlap next to from sigma bond, S and P overlap produces sigma bond, P and P axial overlap produces sigma bond. Here S, P nothing but the orbital, S orbital with another S orbital, P orbital with another P orbital, or S orbital of one atom with the P orbital of another atom. So this overlap takes place actually produces sigma bond. But in this case only one type of overlap, that is P overlap, P lateral overlap. P orbital from one atom and another one P orbital from another atom. They overlap takes place laterally, produces pi bond. As that it is one thing clear. What is that thing? In case of a sigma bond, S orbital and P orbital both are involved. Okay, but in case of a pi bond, only P orbitals are involved. We can't find any presence of a S orbital. So that is the point we have to make. And number of sigma bond, if it is found between two atoms, only one. So number of sigma bond present takes place between two atoms, maximum only one, not more than that. Okay, but number of pi bond may present, may not present. Pi bond may be 0, means no pi bond, or it may contain one pi bond, or it may contain two pi bond. But maximum number of pi bond present, or it takes pi bond formation taking place between two combining atom is 2 and minimum maybe it is 0. So either 0 or a 1 or a 2 number of pi bonds present, but number of sigma bonds are always 1 and that is compulsorily present. So sigma bond compulsorily present, but pi bond may present, may not present. That depends on the nature of the combining atom. Okay. So that is about the major differences or points with respect to sigma and pi bond. Now let us look about how the overlapping taking place. How the overlapping of atomic orbital actually observed as well as laterally observed. Okay. Now let us go with the overlapping of atomic orbital. There are totally 4 categories of overlaps. Broadly 2 types: axial overlap and lateral overlap. But if you go with this specifically, SS overlapping, SP overlapping, PP axial overlap, and PP lateral overlap. So here SS overlapping normally it is axial. Okay. And then PP over SP overlap, that is also axial. So totally 3 axial overlaps are there, 1 lateral overlaps are observed. So 3 axial overlaps are SS, SP, other one PP. S orbital of one atom with S orbital of another atom. S orbital of one atom with P orbitals of another atom. P orbitals of one atom with P orbitals of another atom. Similarly, P orbitals of another atom with the P orbitals of another atom. There is a lateral overlap and also axial overlap. One can find. Now let us see how actually observe and what is schematic representation. So you know S orbital shape is spherical. This is the shape of S atomic orbital. Okay. And this is the shape of another S atomic orbital. Let us say this is the S atomic orbital from one atom. This is another S atomic orbital of another atom. You know atomic orbital should contain an unpaired electron and they will involve in the bond formation. And normally unpaired electrons are designated by symbol this. So half-headed arrow mark. Half-headed arrow mark tells about unpaired electron. Unpaired electron. An orbital with a single electron called unpaired electron. So bond formation need 1 electron. In the previous example you will find 1 electron of hydrogen overlap, or you can say share with the 1 electron of the hydrogen and 1 electron of the hydrogen with the and 1 electron from the chlorine and one singly from nitrogen to another nitrogen. So 1 electrons are needed. So S orbital with S orbital, if it is overlap actually that will produce us S overlapping. So this is the S and then S overlapping. So what happened during overlapping? So this is the 1 electron from this S orbital, this is another electron from the S orbital. So 1 electron from one S orbital, another 1 electron from another S orbital. They overlap. What happened? There is a pairing taking place. So there is a pairing. So this is the direction one can find. So 1 above, another one is the below. An orbital with the 2 electrons also. This is the symbolic representation. So yes overlap formation taking place. Okay. Any of the axes they overlap because spherical shape S orbital, all the probability of finding electron density spread in all the 3 axes. But if you go for SP overlapping along axial, this is the S orbital with 1 unpaired electron, okay, from one atom, and this is the P orbital. You know shape of P orbital, dumbbell shape with 1 unpaired electron. Okay, so here that unpaired electron symbol upward arrow mark, half-headed arrow mark, other one downward. That means the spins are opposite in the sign. So how they overlap? P orbitals overlap produces S orbital and this is the P orbital. So this is the SP overlapping. SP overlapping. S orbital from one atom, P orbital from another atom, overlap produces SP overlap, and this is action. Suppose if x-axis is used from the S orbital, the P orbital also present x-axis. Okay. Suppose if y-axis used from the S orbital, that P orbital must be y-axis. And if z-axis used from this S orbital, that P orbital their axis must be z. So as the axis must be same while overlapping in case of an axial overlap. But in case of a PP axial overlap, there are 2 dumbbells are there. This is the one P orbital with 1 unpaired electron. This is the another P orbital with an unpaired electron. Okay, and they overlap actually along an axis. Let us say both are present along x-axis. What happens if both are present along x-axis? Axial overlap taking place. This is the one P orbital, and this is the another P orbital. They overlap actually produces PP axial overlapping. So here if p orbital present x-axis, it should be p orbital along x-axis. Suppose this is a pz orbital, this must be pz orbital. Suppose if it is a py orbital, it must be py orbital. That means same axial orbitals are necessary for overlap. Since you know px, py, pz, these three are perpendicular to each other and the same axis needed for axial overlapping. But in case of a lateral overlap, let us say this is the one p orbital along the z axis may be present, okay, and this is another p orbital present along z axis with another electron present. Now what happened? If these two overlap laterally, so if it is undergoes lateral overlapping, like that structure will be written. So it's just like writing number 8. So this is the p orbital, this is the another p orbital, and these are present not along the axis, they are present lateral or parallel to the axis. So like that overlapping that is taking place. So this shows p lateral overlap. So above three are axial overlap, but last one is the lateral overlap. So like that overlapping of atomic orbital taking place. And wherever the axial overlaps are there, in those cases, first case, second case, as well as third case, there is an axial overlap. In all the three cases, there is a formation of a sigma bond. But in the last condition, what is that in the last case, there is a PP, lateral overlaps are there. The lateral overlapping leads to the formation of a pi bond. So as a result, the first three shows sigma bond formation, the last one shows pi bond formation. So like that where we find sigma bond as well as pi bond through orbital overlapping. Let us go for the identification of number of sigma and pi bond if a structure or a name of a molecule is given. Let's go with some simple molecules. Let us go with first one, hydrogen. If write the structure of hydrogen with one sigma, one single bond and hydrogen. So between two hydrogen atom, one bond is present. And hydrogen chloride, hydrogen and fluorine. And oxygen already observed, double bond with oxygen. Nitrogen with a triple bond with nitrogen present. Okay, let us go with first of these four. And number of sigma bond. Remember, only one sigma bond, only one bond is there, and if only one bond present between atom, and that itself is the sigma bond. So number of sigma bonds are found to be 1, whereas number of pi bond is 0 in the first examples. Pi bond is not there. Okay. And remember one point: if one bond is there, that itself is a sigma bond. If two bonds are there, out of it one sigma and other one is the pi bond. Okay. If three bonds are there, one sigma, remaining two are the pi. Like that, it is possible to find. Look at that. HF, only one bond is there, that itself is a sigma. So number of sigma bond is 1, and pi bond is found to be 0. And if you go with oxygen molecule, double bonds are there, out of which one sigma and other one is the pi. So number of sigma bonds are 1, number of pi bonds are found to be 1. Point to be noted. In oxygen, two covalent bonds are there, isn't it? Out of which one sigma and other one is the pi bond. And in case of nitrogen, one sigma and the remaining two are the pi bonds. So number of sigma bonds are 1, but number of pi bonds are found to be 2. So in case of a nitrogen molecule, number of sigma bond 1, number of pi bonds are found to be 2. And in ammonia, if you write the structure of ammonia, nitrogen present at the center and 3 hydrogen atoms are there. This is the structure of ammonia. And in this case, 3 bonds are present between nitrogen and 3 hydrogen. And here total number of sigma bonds are, all these are sigma bonds. Look at that, even though bonds are 3, but between atom one is there. Here one between hydrogen and nitrogen, one sigma. Between nitrogen and hydrogen, one covalent bond, nothing but sigma. Between nitrogen and hydrogen, one covalent bond, nothing but another sigma. Such that the number of sigma bonds are found to be 3 in this ammonia molecule. NH3 nothing but ammonia molecule, but number of pi bonds are found to be 0. Okay. Similarly, water molecule, oxygen is present at the center. Here there is the presence of the one hydrogen, and here presence of another hydrogen atom. And between oxygen and hydrogen, one bond is there. But total number of bonds in the molecules are 3. So this is one sigma, this is another sigma. So number of sigma bonds are found to be 2, whereas number of pi bonds are found to be 0. So this is the few examples, 6 examples. So let us go with another example. We have sulfuric acid. So all these are somewhat simple example, but let us see little difficulties. So sulfuric acid. For that we have to remember the sulfuric acid, sulfur atom is the central atom. Here there is a double bond O, and there is a one more double bond O. Here one OH, and here one OH is there. This is the structure of sulfuric acid. And if you find the number of sigma bond as well as number of pi bond, how many sigma bonds are there? Look at that. Wherever single bonds present between atoms, that is a sigma bond. If double bonds are there, one sigma and other one pi. So this is the single bond, sigma bond, single bond, sigma bond. Here also single bond, sigma bond. Here also single bond, sigma bond. And in these two cases, two bonds are there. In that, one sigma and other one is the pi. One sigma and other one is the pi. So total number of pi bonds are 2, whereas total number of sigma bond 1, 2, 3, 4, 5, 6. So in case of sulfuric acid molecule, total number of sigma 6, but pi bond found to be it is 2. And in case of acetic acid, carbon atom present here at the center. Okay, carbon, and here is a 3 hydrogen atom. For this carbon with 3 hydrogen atom, and that is bonded with carbon. And COOH means C double bond O and then O and then H. This is the structure of acetic acid. So number of sigma bonds are, wherever single bonds are there between two combining atoms, that is a sigma bond. This is a sigma bond. Fourth sigma bond, fifth sigma bond, and then sixth sigma. Here one more, 7 sigma. So number of sigma bonds in this case going to be 7, whereas pi bonds are only 1. Pi bond is going to be only 1 in case of a acetic acid. And if you go for the methane, carbon atom with 4 hydrogen atoms are bonded. Okay. And here all these single bonds are sigma bond and no pi bond. So number of sigma bond present in methane molecule, CH4 nothing but methane molecules are 4, whereas pi bonds are 4 to be 0. Similarly for ethyne molecule, this is ethyne. I think you may study that structure, and if you write the complete structure of ethyne, there is a carbon, here one hydrogen, there is a carbon, here one hydrogen, but between carbon there is a 3 bonds also. Between carbon there are 3 bonds. So total number of sigma bonds are 1 sigma, second sigma, and here one more sigma is there. But remaining 2 are the pi bonds. So total number of sigma bonds are going to be 3, but pi bonds are going to be 2. So these are the number of sigma and pi bonds. Okay, so like that we can go for the other example. In case of C2H4, ethene molecule, C2H6, C2H6, that is ethane molecule. So it is total number of carbon atoms are 3. So here one hydrogen, 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 here also hydrogen. So here there is 2 in the double bond, all are sigma bond. So as well, single bond, sigma bond, sigma bond. There are total number of sigma bonds are found to be 1, 2, 3, 4, 5, 6, and then 7. 5 bonds are found to be 0. And then in case of propane, if you write the structure of this molecule completely, 3 carbon atom, and to this carbon 3 hydrogen atoms present, and to this middle carbon 1 hydrogen atom, plus 2 hydrogen present, and remaining terminal carbon atom 3 hydrogen atoms are there. Can I count the total number of sigma carbon, sigma bonds are present? Here it is observed that, so 3 plus 2 5 plus 3 8 9 then 10. So total number of sigma bonds are 10, but pi bonds are found to be 0. Similarly, we can go for the phosphoric acid as well as perchloric acid. I will write the structure: phosphorus with a double bond O, and here one OH, and one more OH, and then one more OH. 3 OH groups are bonded, and thereby we can count that. Similarly for perchloric acid, chlorine present at the center, double bond O, and then here is one OH group is bonded, and remaining all the 3 oxygen atoms form double bond. So we can count the number of sigma bond and pi bond for the example number 30 and example number 14.